So the stack is a tightly managed data structure, and Java can maintain very tight scoping rules with a stack. Stacks are great for local variables because by definition we want a local variable to have a short lifetime. The second area of Java's memory is called the heap. Although the stack is a very efficient data structure, it can't be used to store complex data types such as an object. It can only store simple data types like primitives. We store complex objects on the heap. In general, we can think of a heap as being all of the data in our application that isn't stored on one of the stacks. In an application, there is one heap which is shared across all the threads and a number of stacks, one for each thread. The designers of Java realized that most objects are quite big and that most programs will want to pass around objects between blocks of code. By placing objects on the heap, this makes it easy to do. I hope this makes sense. Suppose we have some kind of customer object that could have lots of fields. If this were stored on a stack and we wanted to pass this customer into another method, well, the process could be quite inefficient. We'd need to take a copy into the new stack of the entire object for the new method to use. We'll see in a moment or two that the approach the virtual machine designers took to use a heap instead is much more efficient. All the threads, and in fact all code blocks in our application, can potentially access the heap. So data on a stack is restricted to a thread and can't be accessed by other threads in our application. But data on the heap can be accessed by multiple threads if we choose to program this in a way to allow it. So just to be absolutely clear, the stack is used for local primitives such as ints and doubles, but all objects such as strings, customers, or integer objects will be stored on the heap. For the objects on the heap, however, there will be a pointer to that object, which is the variable reference, and that is stored on the stack. This is an important point to understand, so let's have a look at a simple example. Suppose we have two lines of code within a method, one that creates a primitive int called age and one that creates a string object called name. So the first line of code is going to create a variable on the stack called age with a value of 21. Because it's a local variable, which is a primitive, it's completely contained on the stack. The string, however, is an object rather than a primitive, so this will be created on the heap. A pointer to this object is created on the stack, which is where we give the variable a name. So the memory used by our string is in fact memory taken from the heap, but with the local variable called name is a pointer that lives on the stack. In fact, all data in our application is accessed via the stack, either fully within the stack if it's a primitive, or by following a pointer to the heap if it's an object. Let's have a look at a slightly more complicated object. Here's some code that creates a list of strings, and then we pass that list from one method to a second method. In the main method, we're creating the myList object as a list of string objects. So when the main method runs and this list object is created, there's going to be a reference to the object or a pointer to it created on the stack, but the object itself will be created on the heap. We'll see this in a picture form in a moment. The myList variable on the stack will contain the memory address of the part of the heap that contains the list object. So the rules for how variables are stored in memory in Java are as follows. Objects are stored physically on the heap. The variable holding the object is just a reference to that object, and the reference, if it is held as a local variable, will be stored on the stack. Primitives are entirely local variables. There are no objects for these to reference, so these live entirely on the stack. Now at first this might feel quite complicated, but it's worth understanding these rules because the whole of Java's memory model is built upon this. Let's now run through our list program line by line and we'll be able to visualize what the memory looks like. So at the start of the program we have an empty stack and heap. Now I know that the main method contains a parameter which is an array of strings called args, and this will actually be the first item on the stack, but as we don't actually use that variable in this example, I'm going to keep this picture clear. I'm going to ignore that one. If I was going to be complete, I would really have a box here somewhere in this picture called args. Note that the boxes I've got on screen to represent the stack and the heap are absolutely not representative of their actual sizes. In reality, the heap is a massive amount of storage space compared to the stack.